Barrit Lovelace. He's a licensed professional engineer and has 20 years of bridge design and inspection experience. I'm going to talk, a lot of things are similar to what Steven talked about, but I think the kind of the overarching theme lately is that, we're in the age of big data, and drones are a tool to collect large amounts of data in short amount of times. And I think the real takeaway from the work we're doing is we're now in a place where we can do something with that data, and we can use that data to effectively communicate our inspection results. So it's becoming less about the hardware and more about the data and what do we do with the data, which has been pretty fun because now we're getting good results and good deliverables for our clients. So just some project background. We've been doing research with the Minnesota Department of Transportation, and MnDOT has been very forward-thinking and progressive with drones. We're in the third phase of our research. At the beginning, it was really more about, identifying which drones would work for inspection, the rules, those sorts of things. But really the rules and the hardware are not really the obstacles anymore. We certainly would like the FAA to move a little bit faster, but for the most part, we can do what we need to do within the rules. And there was a question about the timing. The FAA has actually come out with what's going to be called a LANC system, where you should be able to get instantaneous authorizations in your site, and that'll happen over the summer and into the fall of this year. So when we're talking about using a drone for bridge inspection, there's really two things. We're talking about it as an access tool. So our normal ways of accessing the bridge are aerial work platforms or snoopers, under bridge inspection vehicles, man lifts, those types of things. Those are all very expensive. Also, rope access, structure climbing, could be ladders, binoculars, those types of things. So in a way, we're using the drone to access the bridge, and I'll talk a little bit about, in some situations we can even get better access to the bridge using drones, even compared to our traditional methods. But more importantly, I think what we're discovering is that the drone or UAS technology and software is a documentation tool. So, in order to have an effective inspection, you have to be able to first detect all the deficiencies of the bridge. The second is you need to be able to document those effectively. And then the third, and maybe the most important, is you need to be able to communicate those results to your bridge owner or to the person making the decisions on the bridge. And so we do tons of bridge inspections. Most of the time, our result is a report that maybe has the photos in the back and maybe has a database of the quantities and things. Those aren't always the easiest to read or to get information. So I think what we're doing is we're finding better ways to communicate the inspection results through 3D models and some of those other things that I'll talk about. So the technology that's out there right now, the nice thing compared to when we started is that there are quite a few models of drones now that are inspection specific or mapping specific, so they're built specifically for what we're doing. We're using a SenseFly Albris drone and also a Flyability Elios drone, and the two of them together work really well, and we basically can get 100% coverage of the bridge, which is something we couldn't do in phase 1 and phase 2. But some of the features that we look for, we want the drones are object sensing, so we can sense and avoid objects. But the other thing is we can actually lock onto the object. So when we're collecting data, we're collecting it at the same distance, and we're using the sonar to do that. The drone, really needs to be capable of looking straight up for doing bridge inspections. Obviously, if you're getting under the deck. Also, it needs to be able to fly without GPS. So again, if we're under the deck, we're not running into problems. Most of the drones now have photo, video, thermal imaging, and there's always a focus on the quality of the images and the photos or the video and the photos. And really, all the drones now get really pretty amazing quality, so that's not really too much of an issue. One of the things we focused on in phase 3 is confined spaces, because most drones won't fly up between beams, won't fly into trusses or confined spaces, And those are the places we really need to be, so we've looked at that technology. Our goals for the project, we wanted to look at putting together an inspection policy list, the cost effectiveness of doing this, and anytime we can reduce snooper use or reduce traffic control, we're going to save a lot of money. The safety is also an improvement, so anytime we can change our access method or especially reduce traffic control, we're improving safety by quite a bit. And then also the emphasis on the data presentation and analysis. So this is the confined space drone that we're using. This is a video. I'm not sure if it needs to be clicked on. Okay. Well, maybe the next one will play. But so we're using this Helios drone, which is a ball drone. It's called a collision tolerant drone, and so it has a cage around it, and it can can bump into things, so we can get it between beams, we can get into box girders. In this case, we had a box girder with a hatch, and we were able to fly up into the hatch and inspect the box girder without ever entering the hatch, so we have safety improvements and increased access. So this is another video of a beam inspection. So one of the things we've identified is that the collision tolerant drone works really well for getting up and inspecting beam lines of bridges. And, so 90% of our bridges are just multi-beam bridges. We're either, most of those we're probably not putting a snooper on anyway, just because the cost is so high and the risk is low. But we can really easily get up in between the beams and inspect those beams with the drone. And it's cheap and it's fast. And what we've really pushed is, we're still inspectors. We still have a responsibility to ensure the structural integrity of the bridge, and we're responsible to determine if the data that we're getting, the information that we're getting, is good enough for the inspection. And if we don't, if we see something in the video that we're not comfortable with, we're not sure what's going on, then at that time we can get up and look at that specific location. So maybe instead of putting a snooper on the entire bridge, maybe we're just putting it on the areas that we're concerned about. Our SenseFly Albers drone has a infrared camera built in. So this is a bridge where we went out and chain dragged the bridge. We flew it with the drone to, see if we could get the infrared to correlate. And it correlated really well. The infrared on a drone is really no different than infrared that we use, handheld infrared or those things. The quality is the same, but the real benefit is you can get the drone in a much better position to kind of look at the entire deck and make a map of the deck. This is the screen we see when we're flying the drone. This is again the Albers drone. And so we can go out and we can map a bridge. And in this case, it probably took about 15 minutes to map this site and maybe a couple hours to process it into this dimensionally correct 3D model. So it's a really efficient way to collect a lot of data and make that data useful. And then in fact, in that video, that was all autonomous, so the drone was flying by itself the whole time. So this is another bridge we did. It had a deck that had a lot of delamination, so we went out there, we flew the entire bridge. We can take hundreds of photos of the bridge. We can put all those photos into software. The one we're using is called Pix4D. And so we get this model of the bridge. We can then go in afterwards and measure up all the delaminations. And so we're getting much more accurate dimensions. So if you've ever tried to measure D-lambs in the field, I mean, you're probably lucky if you're getting within 20 or 30% because they're just such odd shapes and they're hard to measure. But so now we can measure them more accurately and better compare from inspection cycle to inspection cycle if there's things are changing. And the other neat thing is when we put it in the model, we have a complete 3D model, the top, the underside. So if we click anywhere on the model, it'll show us all the photos of that part of the bridge. So it acts like a 3D photo log, and so we no longer have to label, each photo, which is extremely time-consuming and very difficult to navigate, and find the photo that you want in a paper or PDF report or a database. The other cool thing is so if we click on a DLAM that's on top of the deck or a crack, it'll show us all the photos of that spot on top of the deck. There's maybe 5 or 10 photos that'll show us, but it'll also show us the photos underneath that correlate with that area. So, if you see efflorescence on the bottom, you can correlate it with the crack on the top. And so it's a really good way to correlate that data. So this is just another bridge where we created an entire 3D model. Again, this probably took maybe an hour in the field to collect the data and maybe just a few hours in the office to process that data. And it's all dimensionally correct. In this case, we didn't even use ground control. So for the most part, when we're doing a bridge inspection, we don't need to use ground control. Our model will be accurate by itself. It might not be exactly in the right place in the world, so you might not have absolute accuracy, but you have very good relative accuracy. We put out a little scale, and then we can measure it in the model to make sure that the model is accurate. And it's amazing how we'll get it within 100th, and that's just using the camera parameters and the GPS to get it that accurate. So some of the other things we can do with the data, we create these 3D models of an entire bridge or just a component of the bridge, and then we can take those models and extract orthoplanes or orthomosaics from it. So in this case, we had a pier cap that had a lot of cracks and deficiencies, and so we flew the pier. Maybe took 50 photos of the face of this pier, and then we go in and just tell the software we want one orthoplane of this pier face, and so it basically just creates one image of the entire face of the pier. So instead of having to page through different photos or click through different photos, you have one photo that's dimensionally correct, and you can measure and either include that in the report or just have that as a deliverable. And so then you can see the accuracy. So as we zoom in, the quality is the quality of a single photo, but it's in a much larger format. This is just an example of a retaining wall that we did, and this, again, just took 15 or 20 minutes to fly it, and this is a 3D model, so we can measure all those cracks and spalls and DLAMs and things, and and then we can take that model and we can annotate it for the inspection also. This is a model of a pier in Minneapolis. So you can imagine going out there with paper and pencil, or maybe you have a tablet with a PDF, and trying to annotate all those deficiencies is pretty daunting and takes a really long time. So there's kind of two workflows that we're doing is, we're creating the model first before we actually do the inspection, and then we take that model out with us in the field, and then we use the model to annotate all our results. And then that way we're not trying to measure, and say, well, this deficiency is 2 feet down and 3 feet over, and it's this wide. That gets really cumbersome. So we can just annotate it right on the model, and we don't even really need to worry about dimensioning it in the field because we have those dimensions already. So it's much, much faster. And the other thing is this one wasn't created with a drone. It was just created with was literally my phone camera. So even without a drone, you can take advantage of some of this technology that is out there to create models and create deliverables. This is an example of this is the Stone Arch Bridge in Minneapolis. So we went out and flew it, and there's going to be a rehab project, so we're looking at different ways to document the condition of the bridge for the contractors, et cetera. And so we went out, we flew it, we take all these photos, we create this 3D model, and once we have that, we have all these really neat deliverables, and we can even share this model on the cloud with a contractor, with the bridge owner, and that way they can go in and measure things and look at individual photographs or zoom in and look at individual deficiencies. In this case, we made an orthoplane of the face of that bridge, so we have a huge photo, and we can zoom in and get a lot of detail on that photo. And I'm not a big advocate of just going out and flying the bridge and doing your inspection in the office, but in this case, I mean, you really can get a lot of information for the inspection just from the model. And so maybe what you're doing is going out, getting that model, annotating it in the office before you go out and do the inspection, and that way when you're out doing the inspection, you're just verifying things, and you're maybe using your hammer to sound things that you're suspicious of. So it saves a lot of time in the field. I don't think there's really any situation where you're going to completely replace your inspection with the drone. I think it's more about plugging it into your workflow to make it more efficient and make your deliverables and the quality of the inspection better. And so I talked about how we can share this information. So one of the struggles we had, at least at the beginning of this phase, is we were collecting all this data, we were creating all these really cool models, but we couldn't share it with our client because they're 10, 20, 50 gigs of data. And so it was really hard, and if they didn't have the software, it was difficult to share it. But now the software we have and a lot of the other ones have cloud sharing platforms. So we literally can just send this link to our client. They can go in, they can look at all the deficiencies, they can look at all the photographs. So if they're interested in a specific part, they can click on it, it'll show them all the photos of that area. So it's a really powerful way to share large amounts of data without having to, email it or put it on a hard drive or that kind of thing. This is another example. This is a pier that we did an inspection of for Paul Pilarski at MnDOT. So we go in, we create this 3D model. In this case, the workflow is a little bit different, where we did the inspection first, we marked all of our deficiencies on the pier itself, and then we flew it. And that way we can go back in the office and measure all those in the office. We create this 3D model that we can send to our client, and they could go in and measure stuff or look at specific areas more closely. So instead of trying to page back and forth and look at a photo log, it's all just a click away. And so this is the way we traditionally do it. On this project, we were kind of doing it both ways. There's nothing wrong with this, but it's and this is just one sheet of that pier, so we end up with 4 sheets. But the difference is pretty amazing, and I think that doing it with the model is actually faster than trying to do the photo log and do all the notes and everything. So I think it's faster, and you get a better product. This is a bridge pier we did in St. Paul. It got hit by a barge, so we went in and we scanned it underwater with multi-beam sonar, created a 3D point cloud underwater, and then we used a camera to map the above water portion and brought the two together. And so you can see the fracture line of the pier, and without having the top part, it's sort of hard to see where that fracture line is, but being able to marry the two really makes it obvious where that fracture is located and where it goes. This is just an example of a asset inventory. Stephen talked about this, but being able to fly a corridor, pick out your assets, you can measure them, you can inspect them, and so it's a really fast and efficient way to identify your assets in the corridor, if it's bridges or signs or guardrail or any of that type of stuff. So I think the application for this is really pretty profound. So one of the other interesting things that we found from our project, I talked about how we're utilizing big data. The interesting thing to me is that there's a lot of companies getting involved. We've worked with Honeywell quite a bit, and so they're spending a lot of money and a lot of time to develop drone technology that's specific to inspection. And we're starting to work with Honeywell also, and Honeywell is doing the same thing. And I think it's really neat because we're going to get to benefit from those endeavors. So, they're finding ways to process our data, to make our workflows more efficient, and and we're working with them to help them understand what inspectors and engineers need out of the process. So it's really been fun to work with them. We've also worked quite a bit with the drone manufacturers and suppliers, and they've been really receptive to getting feedback from us and making changes and improving their products so that they're more useful for us. So that's been a lot of fun also. So our conclusions, we really feel like there can be an improvement in safety, especially when we're removing lane closures. And I would even go so far as to say that, if we're looking at an inspection and we can get as good or better data with the drone and we can make it safer, I think we almost, we have a responsibility to do that. So we have a responsibility to our inspectors and to the public. If we can make it safer, we should be looking at that. The image quality now is really good, and we can identify defects pretty easily. But it's still up to the bridge inspector and the engineer to determine if that is good enough. And if we don't feel like it's good enough, then we need to get up and look at those individually. They're definitely cost effective. The Albris drone, I think right now is around 15 or 20,000. It started off, we bought it for 40, so we got the early adopter fee, but they've come down a lot. The collision tolerant drone is about 25,000, and that's expensive, but compared to snoopers and traffic control, it's really pretty insignificant. We can use them for pre-inspection information. So, we're not necessarily replacing what we're doing, but just using it as a tool for inspection. We can use both drones and handheld cameras to take advantage of this technology, which is neat because not everybody's going to be comfortable flying a drone, but everybody has a camera with them out on an inspection. So if you can make models and things of decks without necessarily having to have the drone. The models and orthoplanes that we're creating from the data are really valuable, and I think the real value is going to start to come when we have, we do a bridge deck survey now, and then we do it again in 2 years, 4 years, and we get to start comparing those results, and we'll really be able to determine deterioration rates and those sorts of things, and that is certainly going to help in planning and bridge preservation models. It's pretty amazing the multitude of file formats that we can export. We can do, the orthoplanes, renderings. We can export it to CAD. We can do virtual reality, which I'm not sure is any benefit besides it's cool. But we can do the web sharing. All those models that I showed you, I can send you a link and you can view them on your mobile phone. You can spin the model around, look at things, measure things right on your phone. So it's pretty powerful what we can do with all the data. And with that, I'll take any questions. Jennifer Wells from MnDOT is the project manager. She couldn't be here today. She's at another conference, but she's very good at answering questions and sending people information also. So with that, if you have any questions, I'd be happy to answer them.
Was Pix4D the main processing program you used for all of those 3D images and the mapping and everything?
Yes, Pix4D is the one we've used the most. We've also used context capture, and AutoCAD has one called Recap. There's an Agisoft one, and they're all competing with each other. There's reasons we like Pix4D right now, but they all have their advantages and disadvantages.
And you showed and discussed card or inventory, and showed an image of directly above the highway. And I had two questions about that. Number one is, my understanding is that there are restrictions for drones. I assume we were talking about drones, and I understood that there were restrictions in terms of driving directly over highways. And number two, aren't there battery life limitations that might limit how far you can really go with that kind of an approach?
Yeah, good questions. So the first with regards to the cars is yes, so the FAA rules say that you can't fly directly over people. And in that case, the freeway was closed. So we took advantage of the closure and flew it. But I would argue that, the FAA has they have a process in place where you can apply to fly over people. They haven't been very good about approving things, but they're supposed to be looking at risk and saying that if you can prove that the risk of flying over people is less than the risk of doing it a traditional way, then they should approve it. And in my opinion, at least, if you don't have to close a freeway, it's much less risk to fly a 4-pound drone over the freeway than it is to close a lane or anything like that. And then I'm sorry, the second question, battery life. So, that comes up a lot. It's really our Albers is about 20 minutes. The Elios is about 10 minutes. I would like it to be longer, but it's not a huge restriction. We have lots of batteries. We can swap them out, and we can resume our mission. And honestly, if you're flying for 20 minutes, especially around a bridge where you're flying really close, you kind of need a break after about 20 minutes anyway. So it's not a huge limitation, but I hope it improves.
You mentioned flying confined space and flying into a enclosed box girder cell. Can you comment on just the challenges associated with that? Maintaining line of sight or losing line of sight, and just the navigation in there, and also, do you have any experience, or can you comment on the challenges associated with flying near electromagnetic interference, and how you guys mitigate that?
Mm-hmm. So if the flying in the confined spaces in the line of sight, so first of all, if we're in a confined space, the FAA rules are no longer there. So we don't have to be within line of sight. And in the box girder case, we're flying it in there just based on what we're seeing on the screen. And the one we did was a steel box girder, so the signal propagates through the steel really well. If we were to do a concrete box girder, we would either have to be in the box girder, or we can put our antenna like on a pole and put it through the hatch to send the signal through there. So that's a way to do it. And electromagnetic. We really haven't run into that very much, and I'm kind of surprised because we've heard that from a lot of other people. They'll have challenges around electrical wires, or even just on a truss bridge. There's so much steel that can cause problems with the compass and everything. So I'm not really sure why we haven't run into that. I don't know if our drone deals with that better than others, but it hasn't been too much of an issue.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.